Hello. Um, we are again working on quadratics, and so in this section, we're going to look at something new. Actually, probably the first new thing you would have seen in the A-level course from GCSE. Something called a discriminant. Now, let's set the scene. So last time we were looking at sketching various quadratic graphs. For example, like this one, we considered where the turning point was and the where it crosses the x-axis and the y-axis. And if you look at some examples, what we did last time, okay, we had a fairly normal graph again. If we repeat the same one, it crossed through the axis, right? Particularly the x-axis, here and here, and all was well. But then we ran into some instances where the graph looked a bit like this, where it was above the axis. And weirdly, when we then solved the quadratic equal to 0, we got no solutions. And so what that does is motivate us now to tell us exactly when or what instances does that quadratic graph cross the x-axis, or when it's above or doesn't cross it at all. Okay, so let's have a look at an example then. So let's take probably the simplest sort of quadratic, right? X squared and minus 1 equals 0. Let's just solve it, right? And let me just use quadratic formula. So remember, the quadratic formula is x is minus b plus or minus the root of b squared minus 4ac over 2a. And so if we solve it using the quadratic formula, but therefore x then would be minus 1, because that would be the b coefficient of 1x, minus 1 plus or minus square root of 1 squared, which should be 1, minus 4, lots of 1, and minus 1, over 2 lots of 1s. So 1's everywhere, right? But then we can simplify it to minus 1 plus or minus root. Then we work inside the root. So 1 minus 4 times 1 times minus 1, that's 1 add 4. So that'd be plus minus root 5 over 2. Cool. That's great. And then we'd expect two solutions, right? So x would be minus 1 plus root 5 over 2, and minus 1 minus root 5 over 2. So that plus or minus is giving us the two sort of solutions, right? Okay, cool. Nothing strange there. Now let's adjust our quadratic to x squared plus x plus 1 equals 0. Then now let's try to solve it again using the formula. So x would be minus 1 plus or minus the root of 1 minus 4 of 1, positive 1 this time. So it's mainly the same, but we have a positive instead of a negative at the end in the square root. Okay, if we then work and simplify it by simplifying the root, we have minus 1 plus or minus the root of 1. Minus 4 times 1, that's 1 minus 4. That'd be minus 3 over 2. Hang on. Okay, so what problem have we got here? Well, actually, we have a negative square root. And you should know that minus 3, or root of a negative square root, you have a negative under a square root, it does not exist, okay? Uh, until you, again, I know there's probably going to be some other math students saying, well, yeah, there is. When you look at a field of complex numbers, we do actually study this more deeply, but for normal A level, you need to know uh, in terms of graph sketching and what you need to work with, you won't get an actual answer, a proper answer. So it does not exist. So there are no solutions, right? No solutions to that equation. Okay, so the problem is now where we've got two different sets of quadratics which barely differ from each other, right? Here I'm taking away one, and here I'm just adding one. Not much of change really, but one has they have drastically different outcomes. Where we have two solutions on the left side, and then no solutions on the right side. Okay, and broadly, we know why, right? Because of the fact that we have the square root, which is positive in the left side, so root 5. And on the right side, we have minus 3, so it doesn't allow us to get a solution. Okay, so we know broadly to do the square root, so let's investigate a bit further, right? So let's look at a quadratic formula again. So remember that gives us actually no, I'm going to do it up here. The quadratic formula here that tells us the way to get x with any type of quadratic. So it's a good idea to have a look at this. And so let's consider, why would we not get a solution then? When would that happen? Um, so minus b, okay, well minus b, that will always work. Uh, over 2a, so we're divided by 2a. You may think, well, what if a is 0 maybe? If you have 1 over 0, that won't work. But, well, if a is 0, then ax squared plus bx plus c just becomes, well, a will go to 0, so we get rid of the x squared, bx plus c. We're not really interested in that because that's no longer quadratic, right? So a will always be not 0, so we don't have to worry about divided by 0. That's all fine. So the only thing that breaks down is, again, the square root. So the square root, b squared minus 4ac, is very important then. Because it, as we saw in the left and the right side here, root minus 3, um, we have a negative, so it doesn't exist. But then when we have it on the left side, positive root 5, then we do get solutions. So actually, it turns out then, if you look at the equation, the solution, if whether or not you get a solution to a quadratic, it all depends on the square root. So, and if the square root exists, right? So if it makes sense, and for that to happen, if you have square root of a number, right? Say x, root x, that again, a square root only works when the number is at least 0, right? Because then if you have a negative under the square root, well, that's saying, so if you have like root minus 1, that that can't happen. Put that in the calculator, and it should say, well, error, something like that, because it's not something we can really work with. And so when it's a negative only under the square root, then we can't work with it, which is why this breaks down. And so essentially, it's all to do with the value under the square root. So we can be even more specific then, and instead of the square root, well, actually, it matters what's in the square root, right? Because if it's negative, like I said, it won't work. But if it's 0 or more, then it can work. So it's under the square root is this expression here. And actually, then it's this expression here that actually allows us to determine whether a solution exists, right? Because then if this expression is greater than or equal to 0, solution exists. Great, because obviously it's not negative. But on the flip side, if it's less than 0, solution does not exist. Okay, and what this actually then gives us, then, if I'm going to get rid of this now to make more room, what this actually gives us is actually a method to actually determine right off the bat whether we whether we can actually solve a quadratic without having to go through all the method and all the effort to actually go through solving it, and then at the end say, oh, I got a negative square root, or this calculator's bugging out, so I don't have a solution. So it allows us a way, if I can just compute this expression, to say, yes, you can solve it. Yeah, oh, no, you cannot. So don't bother solving it. It gives us a verification, if you will. So let's have a look at this then. Um, so remember, b squared minus 4ac comes from ax squared plus bx plus c. And we're solving equal to 0. So we discussed that if b squared minus 4ac is greater than or equal to 0, uh, has solutions, right? Because then the square root here would be would be defined, right? Be defined. But then if b squared minus 4ac less than 0 has no solutions. Okay, so hopefully that makes sense so far. So then, if you think about that graphically, if it has solutions, then it's going to cross through the x-axis, right? That's what setting it to zero means. It means when you solve the quadratic equal to zero, it's crossing through the x-axis. Okay, so it has solutions, and then when it has no solutions, um, then it's you're gonna have this sort of situation where it doesn't cross the axis at all. Okay, so in this situation, or if the quadratic looks like this, if it's a frowny shape, it doesn't have to cross through the x-axis. So in this instance, it has no solutions. Let's have a look at our original example. So the left side was x squared plus x minus 1. If we then computed b squared minus 4ac, well, again, a, b, c refer to the coefficients of x squared, x, and the number. So b squared would be 1 squared, and then minus 4 lots of 1, and then minus 1. Well, that's going to be 1 minus 4 times 1 times minus 1. That'd be positive 4. That will work out to 5. And actually, therefore, it's then at least 0, so it has solutions. And we saw it did. You can rewind again if you want to look at that again. We saw it has solutions. It was what, 1 plus or minus root 5 over 2 or something like that. So it has solutions. And then if it has no solutions, again, let's take our other example, x squared plus x plus 1. Then if we compute b squared minus 4ac, um, then we have 1 squared minus 4 lots of 1 this time because it's positive 1 at the end. Well, that goes to minus 3, which is less than 0. So we have no solutions, which is what we got, right? At the end, we got a negative square root, so we knew that we couldn't solve it. So it actually tells us quite quickly, if we compute this discriminant, that it can be solved or it can't be solved. Okay, and therefore it corresponds to whether the graph crosses the x-axis or not. Okay, so yeah, this gives us a more like proper way of determining solutions, right? And so actually, this b squared minus 4ac, that is called the discriminant. Okay. Okay, so we've looked at these two cases here. So it has solutions but has no solutions. But I notice it's greater than or equal to 0. I think we can investigate that a little bit further. What if uh, what if b squared minus 4ac equals 0? Exactly 0. Well, then the quadratic formula, where should I write it here? X minus b, hang on, now I can get rid of it here. There we are. Make room for it. There we are. So if we then do that formula, when we're setting the b squared minus 4ac, the thing under the root to be 0, that means x will go to minus b plus or minus root 0 over 2a. Well, root 0 is 0. And then if we're adding or taking away 0, that just leaves it as it is. So actually, the solution is minus x equals x is minus b over 2a. There's no plus or minus. There's no way I can get two solutions to this. So we only get one solution in the case when it's actually equal to 0. Because then, if I have a 0, then the square root becomes 0, and and plus and a minus is 0. So no matter what we do, we're just left with minus b over 2a. So that means when b squared minus 4ac equals 0, it has exactly one solution. Okay. Um, then if it's greater than 0, and so that would look like as well, if it had one solution, uh, it would have to basically touch the x-axis, right? Because it can't go through the x-axis like here, because then if it goes under the x-axis, it has to come back up, and therefore it will cross again. So it would look like something like this, right, where it touches the x-axis. Or if we did the frowny shape, it would be like that. Okay, cool. So it has exactly one solution. Has no. Okay, but what about when it's exactly greater than 0? So let's do this case where b squared minus 4ac is greater than 0. Well then, the square root is not going to be 0, isn't it? It's going to be like root 1 or root 2 or root 3 or anything. So we're going to have minus b plus or minus root of something over 2a. Well, that's something. It's a number, right? That isn't 0. So that square root we will have to factor in. So if we have plus or minus, we're adding or taking away a number. That isn't 0, so we can't just say, well, get rid of it because it's 0. We have that would mean if we do plus or minus, we'll actually get two distinct solutions, right? So if we have to do minus b plus the square root over 2a and minus b minus the square root over 2a. So when it's exactly greater than 0, that gives us exactly two solutions to the equation. And so what that would look like is where it crosses the x-axis twice. So it's going to look like that, for instance. Two intersections there, okay? And that occurs then when the discriminant is greater than 0. And yes, so actually that we can break it down even more. And so actually then the discriminant tells us not only whether it has a solution or not or can be solved, but how many as well. Okay, and actually then we can summarize this whole results then quite neatly. Um, get rid of this. So I'm going to restate it, but now we've got the actual results. We've investigated it. So the results for the discriminant is firstly b squared minus 4ac has to be above greater than 0. So has two solutions. Has two distinct solutions. Remember, it's distinct because we're doing plus or minus. That would give us two different answers. I mean, some does call it distinct real solutions as well. It doesn't matter too much. It just means we can actually solve it. Okay. To give us a real answer. Because remember, a real number. Remember, it could be absolutely any number. Remember, we discussed that when we looked at functions earlier on in the chapter. Literally any number from infinity to negative infinity. Any number in between. So when we say a real solution, it can be just absolutely anything. It does exist essentially. Uh, but it's just being a bit specific. Anyway, we have two distinct real solutions. And then graphically, that would look obviously when it crosses the x-axis twice. Okay. Then if b squared minus 4ac equals 0, it has exactly one solution. And again, that's because then uh, the square root would be equal to 0. So we have minus b plus or minus 0 over 2a. But the 0 would be nothing, so we just left with minus b over 2a. That leaves us with only literally one solution. So exactly one real solution. And so it's going to cross the x-axis once, and the way that's going to work is effectively, it's going to just basically touch the axis, like that, okay? So exactly one solution, and then lastly, b squared minus 4ac less than 0, it has no real solutions. So that means there's literally no solutions that exist, right? That is defined. So then it's going to look like it's going to be above the x-axis, or it could be below if it's a frowny shape, okay? But it has no real solutions in that instance. And so effectively, that gives us a piece of theory that now we can use to say, well, very quickly, if we're given a quadratic, we calculate this b squared minus 4ac, and depending on the sign of it, it tells us whether it's solvable or and how many solutions if it is. Okay, so there's one or two solutions. And it also allows us to quickly visualize what the quadratic would look like. So in regards to whether it crosses the x-axis or not. Okay, cool. So let's put that into practice then. First of all, it's asking us to find the values of k for which f of x is x squared plus kx plus 9 has equal roots. So when the roots are equal, well, that basically means there is only one solution, isn't there? Okay, really, because say if you have two roots that are equal, the only way that can happen is if the square root is 0 again, because then if we're doing plus or minus 0, that's still the same thing. But then if we have plus or minus, say 1 or 0.01, for instance, that plus or minus is different in that instance. Plus in 0.01 is not the same as minus 0.01. So what that means is when you have equal, and we can annotate this in a book, so exactly one solution or equal roots, okay? But that as equal roots just means effectively it has to only be one proper actual solution. So if it has equal roots, the discriminant, which is b squared minus 4ac, has to equal 0, okay? Therefore, well, we can compute the discriminant in this case. So b squared is the coefficient of x. Well, that's k. Again, k is just it's a placeholder for a number we need to find, but that's okay. So we can work with that. So b squared is k squared, right? Minus 4, lots of a, which would be, well, the coefficient of x squared is just 1, so it'd be 1. And then c is the number at the end, which is positive 9. And therefore, we have to set this to 0 in order for there to be equal roots. And essentially, this gives us a solution, an equation for k, right, that we can solve. So we can simplify this. So k squared minus 4 times 1 times 9, that's minus 36. Okay, okay. Then I can solve this. So if I move the 36 to the other side, I can then square root both sides. So k is plus or minus square root 36, which we should know is just 6. Okay, so we've got two solutions for k, and that's it. So it's asked us to find the values. So it implies there's more than one, and we've got more than one. Cool, so that's it. So therefore solutions are, so k equals 6 or minus 6. There we are, cool. So hopefully you see I can use a discriminant there, and that's fairly common to mix algebra and equations with the discriminant to work out missing values in the quadratic. Okay, let's have a look at another example. Find the range of values for k for which that quadratic x squared plus 4x plus k equals 0 has two distinct real roots. So two separate roots, but that means what b squared minus 4ac is has to be exactly above 0, so it has to be greater than 0 for the if you remember back to the formula for that plus or minus the square root to actually be different if you do positive or minus. So when the square root is not 0, okay. So yes. Okay, and by the way, you don't have to, in exam situation, we will look at an exam question in later on in a minute, but you don't have to write the sentence down. I'm just in the aspect of teaching it for the first time. I'm just making sure exactly you know where my working is coming from. Anyway, so the discriminant has to be above 0. Let's compute it then. So b squared, well, that's 4 squared, so that'd be 16, minus 4 lots of a, which should be 1, and c, the number at the end will be k. And so it has to be greater than 0. Okay, then we can simplify it. So 16 minus 4 times 1 times k, it's just going to be 4k. And now this is an inequality. Now we do look at inequalities in the next chapter, but I mean this should be you should be able to recall this from GCSE. What I'm going to do actually, with inequalities, I like putting the variable on the left. I just find it easier to read because then minus 4k is greater than minus 16. Um, because then that clearly says to me minus 4k is greater than minus 16. I find it if we said 16 was greater than 4k, I don't know. I know it means the same thing, but for me, I like putting the variable on the anyway on the left. Anyway, then we can solve this. Well, then I want to get rid of the negative. So I get 4k16. But remember, with inequalities, when you divide or multiply by a negative, or simplify down by a negative, you have to flip the sign. So 4k is less than 16. Then we divide by positive 4, so k would be less than 4. Cool, and that's your answer. So it says by the range of values for k, there we are. So for any value of k that's less than 4 exactly, then that tells us the quadratic will have two distinct roots. And remember then, if we link back, that would mean the graph would have to cross through the x-axis two separate times. Okay, cool. There we are. So now let's look at an exercise problem. So we are given this function h of x is 2x squared and k plus 4 lots of x. So that's the coefficient for x, right? Add k. Then it says for part A, find the discriminant in terms of k. So really, the discriminant is b squared minus 4ac. So we literally just need to basically plug it in and substitute. So b squared minus 4ac, well, the b squared is this coefficient k plus 4. So k plus 4 squared minus 4 lots of a, which is 2. And then the c, the number at the end is k. Then this is just an expansion exercise. So k plus 4 squared, you should know, is k plus 4 times by itself, minus 4 times 2 times k, that's 8k. Then I can expand and simplify the bracket. So k, we would have k squared, k times 4, and then another k times 4 would be 8k. 4 times 4 then would be plus 16. 8, take away 8k. Therefore, if we then simplify this, we get k squared. 8k take away 8k will cancel each other out, so we're left with k squared plus 16. And there we are. That's part A done. Cool. That's a discriminant. Then it says hence or otherwise. Remember, exam tip hence means you need to use your earlier part of the question to answer the next part. Prove that h of x has two distinct real roots for all values of k. So remember, two distinct real roots means what? The discriminant has to be above 0, so it has to be greater than 0. Exactly. Okay, well then, we already computed the discriminant in part A. We have k squared plus 16. Okay, but that's telling us in order to have two distinct real roots, this has to be greater than 0. But it's asking us to prove that. It's not asking us to solve it. It's asking us to prove that for any value of k. So we do not solve it here, because if we were to solve, say, equals 0, which we would do perhaps with an inequality, that would only get certain values of k, potentially. Actually, we wouldn't be able to solve it, because if k squared plus 16 equals 0, then k squared would be equal to minus 16. We can't square root that. Anyway, yeah, it's less simple for all values of k, so we do not think about solving. What that means is then we need to just stare at it and see why it is greater than 0. Well, hopefully you realise we have a square number, right? K squared is always at least 0, as it's a square number. They think back to completing the square, we're used to it quite a lot, where the fact we have a square number means that it has to be positive or at least 0, right? So k squared is greater than 0, so that means k squared adds 16 has to be at least 16, right? Because if the k squared is a minimum at 0, then if we added 16 onto the 0 as a minimum, the new minimum is 16. So that's greater than 16, and look, clearly 16 is greater than 0. So k squared plus 16 is greater than 0 for all values of k. Okay. You didn't need to be this descriptive or write that much, but essentially, hopefully you can see what we've done there. It's the fact that, well, k squared is a square number, it's above 0, so that means the whole expression has to be positive. Okay, because we're essentially adding two positive numbers, so it still has to be positive. Okay, cool. And I'll write that down here actually again. So k squared, adding two positives, because that's essentially what we're doing. Uh, oh, positives gives a positive. Okay, that's essentially what we're doing. Okay, cool. And that's it, right? There we are. Um, cool. So that's sort of the strategy, right? With discriminant. We will look at more examples of using discriminant throughout the course, particularly when you're going to next look at circles in that chapter, a few chapters on. We will be using that quite a bit. But for now, hopefully that made sense, right? The fact we can relate how many solutions there are to the discriminant, and then we can use the discriminant to solve equations with missing values. That's essentially what the method is, right? Okay, cool. I want to look at a really difficult exam question to finish this off. Um, Now, this wasn't the exam question as it was. I simplified it a little bit, and just a little bit, to make sure it's accessible for the knowledge you have now. But it's essentially the same question, exact same skills you need to do. Um, but yeah, so we can actually tackle this now. And it's a really difficult one. It's probably one of the hardest exam A level questions ever been asked in the new spec. One of them, one of the more difficult ones for sure. This was the final question in the A level paper. So if you get this, you really understand discriminant. But I picked this because firstly, I want to show how you could use discriminant in the application wise. But also, there is a limitation to this question. There is a limitation where you can't just use the discriminant. And we'll see that in action. But let's have a read of this. So we are given a graph. Okay, we're given a curve. And we're given a line L, and it's intersects at this point P. Um, it doesn't actually matter what P is. That's for the earlier part of the question, but it's given a sketch of a curve and the line. The curve C we're given as this equation. Hopefully, you recognise that's a quadratic. It's also in completed square form, but yeah. So we have this quadratic, and actually that's telling us this time it's only between certain values of x. And you notice that because if it's a quadratic, we looked at earlier, it would actually go on forever. Remember, think back to when we sketched quadratics earlier, last chapter. It continued on forever as you go down the x-axis, right? But obviously we can't draw infinitely, so we kind of put it off prematurely. But in this question, they've literally just sliced off a part of the quadratic, right? And they're only considering a certain segment of it, particularly between x is -1 and x is 5. So x is what? -1 there and 5 there. Okay. Anyway, so that will be important to note. Okay, then it's told us the equation of a lot of the line as well, which is minus a half x plus 17 over 2. Okay, then it told us another straight line has this equation of minus a half x add k. It's told, and we're told it intersects the curve at two distinct points. Well, that is very reminiscent to the discriminant work we just did, right? And it told us to find the range of possible values of k. Okay, so first of all, this curve, this line. Okay, well, what is this line saying? Why is a minus a half x at k? Well, what? Well, minus a half. Well, they're giving us this line here, and coincidentally, it's minus a half x, which is the same gradient, but they're giving k to be 17 over 2. So this line L is particularly k 17 over 2. Okay. And that's helpful to visualize what the line would look like. But what you need to remember then from GCSE, you would have done this. When we have a general function f of x, if we are adding a number k at the end of it, that is shifting the curve up by k units. Okay. So if we had k 17 over 2, if we then added like 2, it will then move the line upwards like this. Okay. If we then said 17 over 2 add 5, it's going to shift it another like 5 units up to where it was. Okay. And hopefully what you visualize then, got this ruler here conveniently. Um, If we then match the line, that's what I'm doing here. There we are, great. So more or less it matches. So if you have a ruler there, essentially adding k means we can only move it literally up or down. Okay. If k was negative, we'd move it down, right? If it was a k is positive, we'd move it up. That's all we're doing. And so essentially this line, for if we vary k, again remember k is a shifting that line up or down. So in case everything over 2, okay, that's the line we have. But if we increase that, it goes up. If we decrease from 17 over 2, we go down. What we need to investigate essentially when this line crosses this curve twice at 2 distinct points. Well, clearly at P at the moment, it's only crossing it once, so that's not good enough. If we then keep shifting it up, it's going to just remain as one intersection, isn't it? And at the very end, at this tip here, oh, this tipping point there where it crosses at the right side, once it goes beyond here, it then doesn't cross the curve at all. So actually, we actually need to move down then. And so if we keep moving down, eventually, you should notice it crosses the most left, oh, the most left point there, the furthest left. Because then if you match it there, it's going to cross there, but also at this point here, right? So that's when it starts crossing at 2 points. Okay. Then if you keep moving it down even more, okay, it's still going to cross twice, twice, twice. Then it reaches this point at eventually when it crosses once, which should be like there, right? Oh, here. Then once it when it reaches out, it then crosses the curve exactly once. It touches the curve, and then if we go down even further, it doesn't cross the curve at all, right? No matter how long we go down. So essentially, we need to investigate when this line first reaches this left point, which I'll mark as point 1 here, uh, and then it keeps going. Oh, for God's sake, it keeps going down until then it reaches the second point here. So those 2 points are when this line um, crosses the curve twice. So we need to basically work out when this line, those 2 points of intersection, right? At the point where it intersects at point 1 that I've circled and point 2. Okay. Cool. So how are we going to do that? Well, at point 1, first of all, well, point 1, you should notice it's at the most left point. It's the furthest left of the curve. But we discussed this. That's like when x is minus 1. So point 1 is when x is minus 1, right? Then, well, we need to find k. So we can substitute x into k. But the problem is we need to find the y value as well. But we know what the y value is. We can work that out because we're given the equation of the curve. So at x equals 1, well, y is a half x minus 1 all squared of 5. Then that becomes x minus 1, a half of minus 1 squared of 5. So then that would be a half of, well, you can put that in a calculator if you wanted to. So then that would be a half of minus 1 squared of 5. You get 7, okay? So we have the point, so 1 is the point, uh, and we can mark that on the graph, I guess. So it's going to be the point minus 1, 7, right? Uh, Actually, it's a bit. I don't want to make the graph too cluttered. So 0.17. Okay, that's the first point when this line, right, as we've visualized, crosses that curve twice at this point 1. So we found the coordinate. Now we can find k, because if y is minus a half x of k, then if we can substitute that point in, so 7 is going to be minus a half of minus 1 at k. we can just solve that for k now. Loads of k's. So 7 is, well, minus a half times, but that should be just positive a half at k. Therefore, k, if you take away half to both sides, 7 minus a half is 13 over 2. Okay, cool. So that's the k value at the point 1. What about the point 2? Um, well, at point 2, it's not particularly clear what the x value is. The thing is, you might well think, well, it's the minimum point, right, the turning point, but not exactly. We could have this sort of situation where, because the graph is a bit small, it looks like it. But if say the minimum point was there, no, sorry, say the minimum point was here, right? It could be just to the right of it, right? We do not know that. The graph is a bit, you know, it might. It might not, it might not be that clear. We're not that zoomed in, so we can't particularly tell exactly where it is. Might not know for sure it's the minimum point. It might be just to the right of it, something like that. So we need to find another way. And actually, and that's I think where the discriminant's going to come in, isn't it? Um, because if we then go back to our line, if I use my line again, oh, not zoom in. Hang on a second. Do. Okay, let's try this again. If we use our line again, right, zoomed in again. So if we use our line again and match it, if again it's going to cross once, then it crosses twice at the point 1. Then we keep going down, and then it crosses uh, at that point. And actually, that point actually, you notice here. That's not the minimum point. See how about if when we zoomed in, we got a clearer picture. So it's not necessarily the minimum point. The second point was actually there, wasn't it? If we go back, it's about there is that's not really the minimum point. The minimum point's not there, isn't it? So that'd be point 2 actually. But the point I'm saying is it crosses twice. Then at point 2, it's crossing once. Then after point 2 below it, it's crossing none at all. So we've gone from a situation where we're crossing twice to once to none at all. Well, that's describing the discriminant, isn't it? Because remember, b squared minus 4ac is greater than 0, then it equals 0, then it's less than 0. So clearly, when we set the discriminant to be greater than 0, that gives us the values of k above point 2, right? So we go at point 2, anything above it will give us 2 intersections. So that'll be k there. Um, so let's do that then. So let's zoom out. Let's zoom out a little bit then. There we are, I guess. Okay, I'll leave that there. So discriminant, but what quadratic is it? Well, we're not going to just do the quadratic of this and do the discriminant. It's particularly when the line crosses the curve, right? So we have y is a half x minus 1 all squared plus 5, and y is minus a half x, okay? That's your line, right? That's the line as we vary k, as k goes down or up. And then this is the curve, right? So when the line crosses the curve, that gives us the intersection, right? That's what we're interested in. So when we put that together, so that would mean we solve them simultaneously. Again, we do look at that later on in the course as a recap, but you remember this in GCSE. We set the equations together. So minus half x add k is a half, and I'm going to expand it. So x minus 1 squared, very quickly, it's going to be x squared minus 2x plus 1 plus 5. Okay. So So then, if we expand the half out, we're going to get minus a half x plus k is a half x squared minus 2 times a half. It's going to be just minus 1, so minus x plus a half, add 5. Actually, what I can do then, I can times the equation by 2 just to get rid of the fraction. Then I'm going to have minus x at 2k. It's going to be x squared minus 2x, add 1, add 10. So I just doubled every single term there. Then that's a lot easier to work with. Then I can move everything to the right to get a quadratic, right? So I'm going to get x squared minus 2x add x, so that's going to be minus x. And then I'm going to have plus 11 minus 2k has to be equal to 0, because when they intersect, remember, when two graphs intersect, like in this instance, then they are equal to each other. And so we solve them in this way. So solving this gets us the coordinates of the intersection. Anyway, so we put that equal to 0, but this is where the discriminant's going to kick in again, and this resembles the examples we looked at earlier, right? Particularly what value we're looking at when there's two distinct points, remember? So that occurs when the discriminant is greater than 0 to give two distinct points. Therefore, the discriminant b squared is minus 1 all squared, minus 4 lots of 1, and then 11 minus 2k, because that's the number at the end. And that's be greater than 0. And then we can just simplify this. So that'd be 1 minus 4 lots of 11 minus 2k. And then we can expand this out to get 1 minus 44, so times 4 by everything in the bracket. And then we get a minus 4 times minus 2k. That's going to be plus 8k. And therefore we could say if we 8k then, well, 1 minus 44 is negative 43. So then that would be equal to, greater than 43. Okay, if we move the minus 43 to the other side, and then therefore k is going to be 43 over 8. Okay, so that's telling you then the point where k is where the line for that value of k, there's two distinct points where the curve intersects with the line, with this ruler line here. Remember, once again, we visualized by God, is it going to work again? Don't mess up on me now. So if we match it to L, when k is 43 over 8, that's going to be this tipping point at point 2, remember, where the line, this ruler, this line, when we're increasing k, when we're going up by k, going upwards, that's when it's going to cross that curve, two different points, when it then reaches point 1, okay? Then at point 1, remember, we then saw k is 13 over 2 here, right? So actually, this gives us two different different points at k. So k then is between those point 2 and point 1, right? Between those 2 points on the graph here again, point 1 and point 2. That's when the that's when the curve and the line cross twice. So that means the k we're interested in has to be between 13 over 2 and 48 over. So 13 over 2 and 43 over 8. Those are the two values of k at points 1 and 2. Okay, if I would circle that, that's k at point 1 and that's k at point 2. Okay, but particularly at point 2, we saw k was greater than 43 over 8. But then at point 1, well, you might think, well, k has to be, that's the highest value of k. So at point 1, again, the line goes downwards, doesn't it? To then eventually meet point 2. So k has to be less than 13 over 2. But it could be less than or equal to, actually, because remember when when k is equal to 13 over 2, that's when it intersects point 1. But at point 1, it also intersects another point here, if you remember. So there's already two intersections at point 1. So k can also be equal to 13 over 2. And that gives us our two values, right? This gives us our solution. So if we put that together, where k is greater than 43 over 8, therefore 43 over 8 is less than k, but k is also less than 13 over 2. And that is your range of values. And there we are. So notice how most of the work there involved discriminant, but that's a very, very, very hard question. But if, especially for the start of the course, I'm not expecting people inside year 12 to bam, I got it. But if you do get it and you make some sort of sense of that, that's great. But the last thing I want to talk on about this though is actually why we can't just only use a discriminant, and that is purely because we cut off the graph. Again, when we talked about cutting off the graph earlier, because the range of values of x are condensed to just -1 and 5, we're not considering every possible value of x on the x-axis, right? We cut off the curve. So what that means is, if we were to continue on the curve, right? Let me get rid of this now, this top bit. If we were to continue this curve on in the way it was, so it goes like, oh no, it goes like this, right? This bit is missing from the right hand side and the left hand side up there. Hang on, let me bring it down here. There we are. So the curve looks like that, but we cut off the right hand side, right? Because remember the curve would go like that to continue on, and it would also go to the left and continue that way as well. However, we cut off those points because x is between -1 here and 5 there. What that means is if we were to just blatantly use a discriminant, well, the discriminant would tell us there's 2 points when this line here, when it goes strictly increasing. So if we go up then and continue up, then if we have the line here, that's at point 2, right? Then if we just keep increasing the cut line, it's going to go twice, 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 and there will always be two intersections between the curve, no matter what. So the discriminant only works properly when it's for every value of x, right? When we have the whole quadratic graph, okay? And in every other example, will it say here? Every other example we looked at, x was for it was for all values of x, right? No matter what. So the discriminant just worked. However, the limitation here is as x is restricted to certain values of x, which means it affects the graph as we cut off the graph. So though we need to be more considerate of the values of when there's two intersections. So what that means is instead of just having k's greater than 43 over 8, when we use a discriminant between the line and the curve. So again, the curve would like this. As we that means there's also an upper limit to when the line only starts crossing the curve once at point 1, right? And then once we go further than that, the line will only start crossing the curve once and then none at all. Okay, and that's purely because of the range of values of x is restricted. Okay, because and that means we cut off part of the graph. And so the whole idea is we need to be more conscious in this question, and this is what makes this question very difficult. Is to realise, well, discriminant is not the only tool we can use here because of the fact that it's restricted values of x. So the discriminant is not the only way of doing it. We need to also consider like another bound, right? Which is where which is where the curve uh, branches off right at point 1, which is x is -1 there. And so actually then that gives us two values of k to consider, and therefore we eventually get this here. Okay, so yeah, I mean that's it. So that's a very tricky example, very tricky. I do acknowledge that. Like I said, it was the final part of an A-level paper, one of the hardest questions on the spec. But I thought that was a good question to illustrate exactly how to use that discriminant. A really good application of it, and obviously the pitfall. The pitfall being again that the discriminant because X is restricted this time, that means the curve is cut off at both the right side and the left side. So actually that creates more difficulty, and we can't just blindly use the discriminant and call it a day. Whereas in the other examples, like we saw, they didn't restrict X, it was just all values of X. So we could just use a discriminant there. But yeah, both this example, but also hopefully you can see why we still can use a discriminant, right? It's still a good, powerful tool to work out when there are intersections, right? But anyway, I'm going to leave that there then. And yeah, so I'll see you next time.